Alright, let's go. Number 10. The Octonian problem. In 2018, mathematical physicist Cole Fury at the University of Cambridge was working on a decades-old puzzle: why the standard model of particle physics has the exact particle content it has, and not some other arbitrary set of quarks and leptons. She wasn't trying to overturn anything. She was trying to find a cleaner algebraic language to describe what physicists already knew. Standard physics builds particles from complex numbers, and Lie groups, SU, chosen because they happen to reproduce experimental results. Nobody derives them from first principles. They are inputs, not outputs. Fury found something else. Using the octonions, an 8-dimensional non-associative number system so strange that even multiplication order changes the answer, she showed that a single mathematical object built from the 4 norm division algebras generates the exact symmetry group of the standard model. Not something close to it. The exact one. Her 2018 paper, published while she was a postdoctoral researcher at Cambridge, showed the algebra SU falls directly out of octonionic structure, with the correct number of quark and lepton generations appearing as a side effect, not an assumption. Physicists had spent over 60 years treating the standard model structure as a brute fact to be measured, not derived. The failure parade started immediately. Grand unified theories using SU and SO groups had tried to derive the standard model from larger symmetries since the 1970s, all predicted proton decay at rates experiments never observed. String theory's approach required 6 or 7 extra spatial dimensions nobody has detected. Fury's octonionic approach needed no extra dimensions and no unobserved particles. It also, as of her published work, could not yet predict particle masses or explain why the algebra should describe our universe, rather than a mathematical curiosity sitting unused on a page. If she's right, the reason quarks come in 3 colors and electrons carry the charge they do isn't physics at all. It's arithmetic. The matter making up your body may exist in its exact form because of a number system invented for entirely different reasons a century earlier. Why an 8-dimensional algebra with no obvious physical origin should dictate the contents of reality is a question no one has answered. The next entry lived quietly in string theory for 30 years before anyone noticed what it implied. Number 9. The Langlands duality that turned out to be physics. In the 1960s, mathematician Robert Langlands was working on number theory, proposing a sweeping set of conjectures connecting Galois groups to automorphic forms, a program so vast it's been called a grand unified theory of mathematics. He wasn't thinking about particle physics. He was trying to unify disconnected branches of pure math. Standard practice kept the Langlands program and theoretical physics in separate departments for 4 decades. Number theorists proved fragments of it. Physicists built gauge theories. The 2 fields had no reason to touch. In 2006, Edward Witten at the Institute for Advanced Study and Anton Kapustin at Caltech found that the geometric Langlands program is a direct consequence of S-duality, a symmetry in 4-dimensional gauge theory that swaps strong and weak coupling regimes, the same duality underlying parts of string theory. Their paper, published in Communications in Number Theory and Physics in 2007, showed that mirror symmetry in physics, specifically the electric-magnetic duality of N4 supersymmetric Yang-Mills theory, reproduces the mathematical structure of geometric Langlands almost term for term. A 40-year-old pure mathematics program used to organize entire fields of number theory had been sitting, unnoticed, inside gauge theory equations physicists had used since the 1970s. Mathematicians questioned whether the connection was coincidental. Dualities are common in both fields and can produce superficial resemblance. But the correspondence held up to detailed structural comparison, matching Hecke eigensheaves to 't Hooft operators with a precision that resisted dismissal as pattern matching. No one has produced a physical mechanism explaining why a conjecture about prime numbers and Galois representations should be encoded in the vacuum structure of a quantum field theory. If the connection is real, then somewhere in the mathematics describing how forces trade strength for weakness, a piece of unsolved number theory is already computed, sitting inert in the equations, waiting for someone to know what to look for. What Langlands was actually describing when he wrote down his conjectures in 1967 remains an open question. Nobody expected the next one to survive contact with the Higgs boson. Number 8. Alain Kahn's geometry that built the universe from nothing but space itself. In the early 1990s, mathematician Alain Kahn at the Institut de Hautes Études Scientifiques was developing non-commutative geometry, a generalization of geometry where coordinates no longer commute. Originally intended to describe the geometry of quantum spaces too small or strange for ordinary manifolds to handle. Ordinary physics builds the standard model by hand, choosing gauge groups, choosing particle representations, adding a Higgs field to give particles mass, and tuning roughly 20 free parameters to match experiment. Nothing in the framework explains why those choices were necessary. Kohn, working with physicist Ali Chomsedine, found that if spacetime is modeled as an ordinary four-dimensional manifold multiplied by a tiny non-commutative finite space, the entire standard model, its gauge fields, its fermions, and critically the Higgs mechanism itself, emerges automatically from the geometry, with no separate insertion required. Their model, published across several papers through the 1990s and refined in a widely cited 2006 paper in Fortschritte der Physik, made a falsifiable prediction: the Higgs boson mass. Their original calculation predicted around 170 GeV. When the Higgs boson was discovered at CERN in 2012, its mass measured 125 GeV, a clear miss. The failure parade here is uncomfortable, not clean. Kahn and Chomsedine revised the model, adding a scalar field to bring the prediction in line after the fact, which critics noted looked less like confirmation and more like a rescue. Other non-commutative geometry approaches from Thijs van den Broek and Walter van Swillecom attempted independent derivations with mixed success. The geometry still reproduces the standard model structure exactly. It still cannot cleanly predict the one number that would prove it isn't coincidence. If Kahn's is right, then the very fact that particles exist as separate types with distinct masses and charges is a symptom of space itself having a hidden, unobservable extra structure folded into every point you occupy, including the one you're sitting in now. Whether that finite space is real geometry or an elaborate accident of the math remains unresolved. Ramanujan never lived to see what his hospital notebooks would become. Number 7. The Mach modular forms that count black hole microstates. In 1920, dying of tuberculosis in Madras, Srinivasa Ramanujan wrote to G.H. Hardy describing a class of functions he called Mach theta functions, objects that resembled modular forms, a well-understood class of highly symmetric functions, but broke the rules just enough to defy classification. He had no physical application in mind. He was, by his own account, chasing a mathematical intuition he couldn't fully explain even to himself. For 87 years, Mach theta functions remained a curiosity confined to analytic number theory. Modular forms had known physical uses in string theory. Mach modular forms did not. They lacked the transformation properties string theorists needed. In 2010, mathematician Sander Zweger's earlier framework was extended by physicists Miranda Cheng, John Duncan, and Jeffrey Harvey, who found that a Mach modular form governs the symmetry of K3 surfaces, geometric spaces central to string compactifications, in a phenomenon they named Matthew Moonshine, published through 2012 in Communications in Number Theory and Physics. More strikingly, separate work led by Atish Dabholkar, Samir Murthy, and Don Zagier showed that Mach modular forms exactly count the microstates of certain supersymmetric black holes, reproducing the Bekenstein-Hawking entropy formula with corrections that only Mach modular functions, not ordinary ones, could supply. Every attempt to explain this using ordinary modular symmetry failed outright. Ordinary modular forms simply don't have the right growth behavior to match black hole degeneracy counts. Only the broken Mach version, the one Ramanujan flagged as defective in a letter written while dying, fits, a number system a self-taught mathematician half-glimpsed from a hospital bed in colonial India, with no access to physics literature, may now be the correct language for counting the hidden internal states of collapsed stars. Why his intuition landed on exactly the right broken symmetry a century in advance has no explanation anyone has offered. The next one says you cannot know, in advance, whether a piece of matter as ordinary as a crystal has a gap in its energy spectrum, and that this isn't a limitation of current technology. It's mathematically permanent. Number 6. The spectral gap that mathematics forbids you from ever solving. In 2015, computer scientist Toby Cubitt at University College London, physicist David Presgarka at Complutense University of Madrid, and mathematician Michael Wolff at the Technical University of Munich were investigating the spectral gap problem, determining whether a quantum many-body system, like a chunk of material, has an energy gap between its ground state and first excited state, a property that determines whether the material is a superconductor, an insulator, or something stranger. Physicists had computed spectral gaps for specific materials for decades, assuming that with enough computing power and cleverness, any system's gap could eventually be determined. Cubitt, Presgarka, and Wolff proved the opposite. Their paper, published in Nature in December 2015, showed the spectral gap problem is formally undecidable, equivalent to the halting problem Alan Turing proved uncomputable in 1936. For certain quantum lattice models, no algorithm, run for any amount of time, can determine whether the material has a gap. Every proposed workaround failed by design. Restricting to simpler models pushed the undecidability further out, but never eliminated it for physically realistic systems. Approximation methods could not approach undecidable problems, because approximation implies convergence, and undecidable problems have no convergent target to approach. The result held even for one-dimensional chains. The simplest case physicists had assumed was fully tractable. This means some real materials, sitting in labs today, may have a property, gapped or gapless, that is not merely unknown. It is unknowable, in the same sense that some mathematical statements are true but unprovable. Your understanding of ordinary matter has a hard ceiling built into the logic of computation itself. Which materials fall on the undecidable side of that line, and whether one is on your desk right now, is not a question physics can ever finish answering. Gödel wasn't trying to break mathematics. He was trying to save it. Number 5. Gödel's incompleteness. Mathematics cannot know if it is true. In 1931, mathematician Kurt Gödel at the University of Vienna set out to accomplish something else entirely. Prove that mathematics, once and for all, was complete and self-consistent, settling a program David Hilbert had launched a decade earlier. Gödel wanted to close the case, not open a wound. The prevailing assumption, formalized by Hilbert, was that any sufficiently powerful formal system could, in principle, prove every true statement expressible within it, and could prove its own consistency from inside itself. Gödel found the opposite was mathematically forced. Any consistent system powerful enough to describe basic arithmetic necessarily contains true statements it cannot prove, and cannot prove its own consistency without stepping outside itself. His 2 incompleteness theorems, published in 1931 in Monatchef for Mathematik on Physik, ended Hilbert's program within a single paper. In 1936, Alan Turing independently proved the halting problem undecidable using similar logic. In 1987, mathematician Gregory Chaitin showed that almost all real numbers are algorithmically random. They cannot be compressed into any formula shorter than the number itself. Every attempt to rescue completeness failed. Adding new axioms to patch the gaps only created new unprovable statements one level up, a pattern that repeats without end. Restricting to weaker systems avoided incompleteness, but made the system too weak to describe arithmetic at all, defeating the purpose. If Max Tegmark's mathematical universe hypothesis is correct, and physical reality is fundamentally mathematical, then somewhere in the laws governing your body right now there exist true facts about your own existence that cannot be derived from any physical theory. Not because we haven't tried hard enough, but because no theory ever could. What those unreachable truths actually are is a question incompleteness itself guarantees can never be answered from inside. The next entry involves a number 8 times 10 to the 53rd elements large, and no one can explain why it showed up in string theory. Number 4. The monster group's unexpected appearance. In 1979, mathematician John Mackay wasn't hunting for physics. He was examining coefficients in the J function, a classical object in number theory, when he noticed the number 196,884 sitting suspiciously close to 196,883, the smallest non-trivial representation dimension of a group so large it hadn't even been fully constructed yet. Group theory in the 1970s classified finite simple groups as a purely internal mathematical exercise cataloging symmetry, with no expectation any of it would touch physical theory. Mackay's observation turned into an entire phenomenon. The monster group, the largest of the 26 sporadic simple groups containing approximately 8 times 10 to the power of 53 elements, was fully constructed in 1982 by Robert Griess at the University of Michigan. Its numbers kept appearing inside the J-function structure. Mathematician Richard Borcherds proved the connection, called Monstrous Moonshine in 1992, work that earned him the Fields Medal. The proof required constructing a vertex algebra equivalent to a two-dimensional conformal field theory, the exact mathematical machinery used in string theory to describe vibrating strings. Every attempt to explain this as coincidence collapsed under scrutiny. The correspondences were too numerous, too precise, and too structurally deep to dismiss as small-number arithmetic accidents. In 2010, John Duncan and colleagues found other sporadic groups embedded in similar moonshine relationships, ruling out the monster as a one-off fluke. The single largest exceptional symmetry object in all of pure mathematics, larger than any classified group that isn't part of an infinite family, sits embedded inside the same conformal field theories physicists use to try to describe the fundamental strings that may compose your body's every particle. No one has ever produced a physical reason the largest symmetry in mathematics should be the one nature apparently reaches for. The next one connects the distribution of prime numbers to the inside of an atomic nucleus. Number 3. The Riemann Hypothesis and Quantum Chaos. In 1972, physicist Freeman Dyson at the Institute for Advanced Study was having tea when mathematician Hugh Montgomery described statistical patterns he'd found in the spacing between zeros of the Riemann zeta function, a subject with no known connection to physics. Dyson recognized the pattern instantly. He'd seen it before, in nuclear physics. The Riemann hypothesis, proposed in 1859 and still unproved, concerns the location of zeros of a function that governs how prime numbers are distributed. Physics, meanwhile, uses random matrix theory to describe the statistical spacing of energy levels in complex quantum systems like heavy atomic nuclei, a completely separate mathematical toolkit. Dyson told Montgomery the zeta-zero spacings matched, statistically, the energy level spacings of quantum chaotic systems. Mathematician Andrew Odlyzko later confirmed the match to extraordinary numerical precision, comparing millions of zeros against random matrix predictions. In 2017, physicist Carl Bender at Washington University in St. Louis and colleagues published a specific quantum Hamiltonian whose energy eigenvalues, if the Hamiltonian is physically realizable, are exactly the non-trivial zeros of the zeta function, meaning the Riemann hypothesis would follow directly from the fact that energy eigenvalues of real physical systems must be real numbers. Every attempt to confirm the Hamiltonian is physically realizable, rather than a formal mathematical trick, has stalled. Whether such a system could exist in a lab remains unresolved a century and a half after Riemann posed the problem. If the connection is real, the sequence governing whether the number sitting in your pocket right now is prime is the same sequence governing the vibrational energy of atomic nuclei inside your body. Nobody can say why arithmetic and matter would be speaking the same statistical language. Even the equation that built the atomic bomb's underlying theory works by refusing to finish itself. Number 2. The unreasonable effectiveness in reverse. In 1960, physicist Eugene Wigner wrote his now famous essay celebrating how astonishingly well abstract mathematics describes physical reality. He was marveling at success. He wasn't looking for the failure hiding underneath it. Quantum electrodynamics is the most precisely tested theory in the history of science, with predictions confirmed to 12 significant figures. Those predictions come from perturbation theory, an infinite series of increasingly complicated terms that standard mathematical expectation holds should converge toward a single correct answer the more terms you add. Freeman Dyson proved in a 1952 paper that the series does not converge, it diverges. Adding more and more terms eventually makes the answer worse, not better. The theory only works because physicists stop adding terms at an optimal truncation point, a specific number of terms beyond which accuracy degrades, and this partial sum happens to match experiment to extraordinary precision. Every attempt to fully justify this mathematically has fallen short. Borel summation techniques recover some divergent series, but don't fully resolve Ked's specific case. Resurgence theory, developed decades later, offers partial insight into why truncation works without providing a complete first principles derivation. Physics' most successful calculation still runs on an unexplained rule of thumb: stop before the math tells you to keep going. The theory describing the electrons in every atom of your body works precisely because physicists deliberately refuse to complete the calculation that theory demands. Why an incomplete calculation gives a complete answer about reality has never been resolved. The last one was discovered in a board game, and no one can explain why it followed physicists into the lab. Number 1. Surreal numbers in physics. In 1974, mathematician John Conway at Cambridge wasn't researching number theory. He was analyzing endgame positions in the board game Go, trying to formalize which player was ahead. Out of that analysis fell an entirely new number system. Standard mathematics treats the real number line as the largest ordered field needed to describe continuous quantities. Infinite in extent but complete in the sense physicists require. Conway's surreal numbers dwarf the reals. They contain every real number, every ordinal, every cardinal, and an uncountable infinity of additional numbers packed between, beside, and beyond all of them. A number system so vast the reals are a vanishingly thin sliver within it. In 2012, physicist Lawrence Eves at the University of Nottingham published work suggesting that Landau levels, the discrete energy levels electrons occupy in graphene under a magnetic field, correspond to positions within a specific surreal number construction. In 2019, mathematical physicist Matilde Marcoli at Caltech published further work linking surreal number structures to renormalization procedures in quantum field theory. Every attempt to dismiss this as a relabeling exercise, mapping familiar physics onto unfamiliar notation, has failed to explain why the surreal construction specifically, rather than any other equivalent formalism, keeps appearing in these unrelated corners of condensed matter and quantum field theory. A number system invented to score a two-player board game now appears, unbidden, inside the electron behavior of a material sitting in laboratories on the same planet where the game was first played. Why mathematics born from something as small as a Go match should resurface inside the quantum structure of reality is a question that remains completely open. The universe was never confused about any of this. Gödel's gaps, the monster's shadow, Ramanujan's broken symmetries, an undecidable spectral gap sitting inside ordinary matter, none of it sits at the edges of what we know. It sits at the center of our most tested, most confirmed, most mathematically rigorous theories. The confusion was never out there in the equations. It's been in here, in the assumption that understanding the math means understanding the world it describes. Every entry on this list is proof against that assumption. If you want to see more videos like this, click the video on screen now.